So what are you going to walk out of this room with? First and foremost, we're going to start with a foundation of, evidence that the brain actually runs one algorithm. And then we'll start breaking down how the brain does inference. And once we do that, we'll implement it in Scala. So just a little bit of a warning for you guys. I'm going to do something that's a little bit out there. Probably for the next 15 minutes, I'm not actually going to talk about Scala. I'm going to lay some of this foundation so that then you guys have the context to understand the code and the algorithm that we're going to be looking at. So if you want a really, really Scala-y talk, then I won't be offended if you don't want to stick around. So we're starting with this fundamental question. Does the brain run on a single algorithm? This is not a new question. AI researchers have been interested in this for years. It's the holy grail of artificial intelligence. If there is this one algorithm, we can implement it on a machine, and there's no limit to what kind of applications there can be. So some recent developments have kind of led us down this path to believe that yes, there really is one algorithm. And let me give you a couple of examples that might point to that. The first one is actually a story about a man named Daniel Kish, who some of you may have heard of. He was blind at age 2 or 3, and he naturally started doing this clicking sound to locate the objects around him in the room. He got so good at this, in fact, that he can ride bikes. He can climb trees, and he can go out in the wilderness, unexplored territory. So a few years ago, a researcher by the name of Lord Thaler wanted to study what actually happens in his brain. So she took him and a bunch of other experts and put objects in front of them and had them do their clicking sound. She put these guys into an fMRI and watched what happened in their brain while these sounds were being replayed. And as it turns out, the visual cortex was lighting up. So as you can see in this area, just like a sighted person's would. And as a control, they did the same experiment with folks who don't have that skill, and nothing was going on. So just stop and think about that for a minute. For a normal sighted person, the photons are hitting your retinas, and they're going through the optic nerve to the back of your brain where your visual cortex is, right? There's this direct link. For people like Daniel Kish, the sound waves are going through the air, it's going into your cochlea, into your auditory cortex, and then back into the back of your brain. That is a very different pathway, a very different information, and yet somehow the brain can create this visual perception out of a completely different input. So if that doesn't convince you, give you a couple other examples. How many of you guys have watched Star Trek: The Next Generation? And are a fan? Woohoo! All right. And our favorite character, the chief engineer, Geordi LaForge, you know how he's this blind guy and he has a visor that allows him to see. He can see in light spectrums that no human being can perceive, infrared, ultraviolet, and all kinds of radiation. In fact, this is no longer science fiction. This is a reality. So there's a number of interesting projects in terms of sensory substitution. The one on the right here is a vest that is a recently funded Kickstarter project by a neuroscientist named David Eagleman. And this vest basically takes the sound coming from your phone's microphone and converts it into vibrations around your chest. On the right we have a device called the BrainPort, which it has a camera, and it converts that into these little sensory depressions on your tongue. So if you're blind, you actually get some sense of vision. If you're a soldier, you might get a sense of infrared vision, or maybe even 360 vision. So this actually leads us to a pretty compelling hypothesis, which is that the function of your brain is a product of its sensory input. And if you really think about that, what it's saying is your brain, given your brain is made up of a bunch of neurons, there are no neurons that were built for hearing. There are no neurons that were built for seeing. They actually learn to see or learn to hear based on what sensory inputs they're connected to. So as a computer scientist, this is a fascinating question, because what it means is if we can crack that nut, we can develop machines that have senses beyond any human capacity. So imagine a machine that its senses are internet traffic, and it can route internet traffic, or it can detect that there's an intrusion and stop it in its tracks. So these are some of the amazing things that I think are going to be possible in the next few years. We're going to test this hypothesis a little bit today, and I'm going to use a very visual example, but keep in mind that this is something that applies to any of your senses. So we're going to do a little test and see who's awake. I'm going to show you a picture. You might have seen it before. As soon as you recognize some object in the picture, just raise your hand. Don't say what it is. Just want to see how many people can recognize something. Not everybody will get it. So here it is. Okay, either a lot of you have seen it or you're really quick, or you've seen it before. I'll show it for a few more seconds, just in case. Dick is still trying to figure it out. Okay, all right, I'll say a word. I think that is a tree, but I will say the word Dalmatian. If any of you that didn't get it before and now see it, raise your hand if you just saw it. Okay, that was your brain at work. So yeah, okay, you see it now. Good job, yay, good job, Dick. Okay, so how did your brain do that? That was a pretty amazing feat. This is a very noisy image. There's just so much going on and there's not a lot of signal. But somehow your brain figured out that there was this dog in here. So there's actually three pretty key ingredients to this: pooling, inhibition, and hierarchy. So I'm going to break down each of those, and then we'll look at how to implement those in Scala. So yes, I will get back to the Scala. So pooling is just kind of a shorter way of saying coincidence detection, right? When you're looking at this image of this dog, you're going to see all of these little features, right? Over here, there's an ear, there's a collar, there's, an outline of the back. And so what your brain is doing is detecting all of these little coincidences and pooling them together into a higher level representation. So let's translate that into an actual language that a machine can understand. And so what we do is we form a sparse distributed representation. Well, what does that mean? Your brain is comprised of billions of neurons and a bunch of, and even more billions of synapses. At any given time, some very limited subset of those neurons are currently active or firing. So if you squint at it, it almost looks like this sparse vector of activity happening. And there's a couple of key properties that we need to hold true. So in this sparse vector, the size of the vector represents how many neurons you have, and then each on bit in that vector represents a neuron that's currently active. And in terms of distribution, you want the information contained in that firing pattern to be distributed across your neurons. You also want very similar similar patterns to have a high degree of overlap. So they don't have to be identical, but they should be similar. So in this example, you've got a spot over here and a spot over here, and these are kind of similar, and they have a high degree of overlap, but they're not identical. So fundamentally, if we can take some object from the outside world, an image, text, it doesn't matter what it is, and convert it into this representation, we now are kind of at the gateway of this algorithm that we're going to build. So pooling, so a pooler is going to look at some set of neurons as input, and it's attempting to pull a pattern out of that. And we are modeling these connections between these poolers. So the idea is you apply Hebbian learning, which maybe some of you have heard of. It can be expressed simply as fire together, wire together. So if your input is active at the same time your pooler is active, you want to strengthen the connection between the two of them, right? Say, I'm reinforcing the fact that this is a coincidence. On the other hand, if your input, you have a connection to an input that's not firing at the same time as your pooler is, you're going to weaken that. So eventually this pattern, these red ones, will kind of come out of the noise. These other guys represent noise that is just not coincident enough with the pooler to actually be recognized. So properties of poolers, they have a few nice properties. The noise resistance I mentioned. There's also some amount of tolerance to loss of signal. So if you have an incomplete signal, like in this example, this guy's missing, well, it's enough information that you can complete that pattern just as your brain did with the Dalmatian picture. So the second element is inhibition. It would be really nice if you just had this one pooler and it always just went off when you had a dog, when you saw a dog, right? But that's not how it works in reality. You have billions of these things. So they need to work together somehow, right? How do you get these sparse representations? So you take a pooler and you put these into groups. We call them layers. If you've done deep learning, you kind of know what a layer is. But you can just arrange it as a 1D vector or a 2D matrix. So now we have a group of poolers. The idea is you're trying to represent, you're trying to disambiguate, right? If you're looking at this very fuzzy picture of a dog, you might have thought, oh, maybe it's a spotted cow or maybe it's a spotted horse. But your brain made a very clear choice. So the idea is the best match wins, right? So these things are mutually exclusive, right? So you want the dog, which has this kind of floppy ear and collar feature, to beat the cow, basically, because the cow just, maybe it's got a little bit of overlap there, but it's not entirely, doesn't entirely match. So by using inhibition, you're actually turning off neighboring poolers that don't match as well to the input pattern as you match. This is just a pictorial example of what that might look like for SDRs. So you have a blue pattern with 4 overlap and a red pattern with 6, and the red pattern wins and says, hey, I got this, you guys, turn off, right? So really amazing properties that come out of this. First of all, you get this beautiful self-organizing property where you don't get a million poolers all learning the same thing, right? If one guy says, hey, you guys turn off, I got this, the other guys are going to go learn something else, some other coincidence. If you start introducing locality to the mix, you're going to get similar concepts that are mutually exclusive pooling in the same area. And the other thing I love about this is it's actually kind of a compression algorithm, right? Sparsity emerges out of this. You're taking tons of sensory input and your representation of that is highly compressed. Autistic patients actually don't have enough inhibition, and so they might actually get to a point where something happens over there and they don't know what to focus on, right? You're going to go look over there. So one more thing, hierarchy. If you know about pooling, it's pretty straightforward to add a hierarchy to it. Hierarchy is really just given one layer, take its firing pattern or the winners of the inhibition race and feed them up to the next layer, right? So with the dog, you might start with these visual little shadows and edges that are very vague, and as you go up the hierarchy, you're going to form more and more complex representations. Here's the cartoon diagram, so you can kind of see that as you're going up the hierarchy, you're not only compressing, but you're seeing that there's coincidence of patterns. So the result of that actually is that you get increasing stability of activation as you're going up this hierarchy, right? If you think about it at the very basic level, your eyes are moving around the room several times a second. You're hearing different sounds. So the activation of those are going to be drastically different. But your brain is perceiving a very stable reality, right? And that is an artifact of the hierarchy. So before I move on, I want to give a quick shout out to Jeff Hawkins' book again on intelligence. If this was an interesting sort of taste of it and you want to learn more, I definitely recommend reading into that book because he gets a little bit deeper in the concepts. And also, some of these concepts are implemented in a project called NuPIC. There's a C++ and Python and a couple other languages. And so you can actually get your hands dirty in that. As far as I know, there's no Scala implementations other than the one that I'm going to show you today. So let's implement. I have to have the obligatory why Scala slide. It's actually pretty efficient for us to use Scala on multiple dimensions. We're actually doing a lot of R&D, and the beauty of using Scala is that the time that we're spending is basically focusing on building that algorithm, and there's very little time spent actually writing code, because as soon as you have the idea, within a couple hours you have the code written. So that's beautiful. And we have rewritten it a few times, and that generally takes just a couple days. It's not this, onerous thing. Also, we're doing a lot of experiments as well. So we're trying to tweak parameters or try out different variations of the algorithm. And the runtime is fast enough. You can do, 100,000 iterations in just a few seconds. So lots of efficiencies gained. I love the compactness of the Scala. So the demo you're going to see, yeah, it is under 180 lines of code. So I find that pretty amazing. And then I honestly use the compiler as my debugger. I mean, it does most of the debugging for me. So if it compiles, it's probably going to work. So what was the design approach? It's actually entirely immutable, which if you think about what we're doing, we've got these neurons with these firing patterns that are constantly changing, and we have these connections that are constantly being modified. Well, we're actually doing that in an entirely immutable way. It turns out that it's really convenient to use case classes as kind of the de facto immutable data structure. And each case class can modify itself, so we'll see how that looks. And also, conveniently, most of the operations we're doing is really just transformations on collections, right? If you're computing the overlap between the input pattern and the pooler, then that's pretty much just a set operation. So a lot of convenient things come out of there. Other thing I want to point out, given that we have this connectivity between poolers, we needed to avoid having bidirectional references being passed around to construct the object graph. So all of it is based on addressability. And the approach. This is kind of the lessons learned slide a little bit. So my background is actually building the nuts and bolts of back-end systems. And so I had a hammer, and I really wanted this thing to be a nail. So I thought, okay, I'm going to use Akka because Akka is awesome. And I'm going to put every single pooler into its own actor because they're passing these messages back and forth, and that was going to be great. But it just was not great. So kind of realized along the way that we needed to understand the core of the problem we were trying to solve. And so it was a big reset to go, okay, let's actually solve this in the simplest way possible and not worry so much about the asynchronicity and the scale. So in fact, the implementation you're going to see doesn't really use frameworks, asterisks, except there's a reactive parallelization example if you want to see that. And so I'm always asking, can I simplify this further? Do I really need this extra framework or this extra bit of logic here? Okay, actually I'm going to switch away from the slides and just take you through the code because I think this just feels more natural. What I want to do is show you guys the data model first, and then sort of the data flow, and then we'll kind of see where things go. So this is the outermost class. It couldn't get much simpler than this. What you're seeing here is this model which holds the entire hierarchy. The hierarchy is very simple right now. It's just this stacked list of these layers that feed into one another vertically. There's nothing in the algorithm that would prevent a more interesting hierarchy, such as two layers converging into one or one layer diverging. So it's as long as it's like a DAG, you can basically support it, right? in the real world, you're going to have a bunch of different sensors, so this kind of hierarchy will be needed. Inhibition is really just a behavior, right? It's the strategy for picking these winners within the layer. So let's dive into the next level. Oops, where did I get that? I'm going to go to layer. So a layer is just a vector of poolers, right? And there's a set of active bits for the layer. I should explain what this is. So I've been to a couple talks these last couple days about using the, strong types and let the compiler do validation for you. So this is a big no-no. But what this is basically representing that sparse distributed representation. You could think of that as an array of Booleans where the on bits are in fact the ones that are currently active. But it turns out that because this is sparse, it is far more efficient to represent this as a set of addresses to the poolers that are active. So it's a much more compact and efficient representation. So that's what that is. By the way, am I losing you guys, or are you kind of staying with me? Okay, good. Okay, so what is a pooler? The pooler just has its own index, which is the address. And it has these connections. So the connections are really just an address that goes down to the lower layer, what's on the other end of this connection. And then it has this thing called permanence value, which I didn't talk about in depth. Permanence is essentially just a number that we use to determine whether a connection is actually in existence or not, right? We're using this to figure out the statistics of the input. So you'll notice there's this threshold under which we're just discounting the connection entirely. Okay, it's probably time for a couple of little things that I learned along the way. How many of you guys have used the caseClass.copy method? Okay, a bunch of you guys, but not everybody. So this is worth saying if you haven't used it. The caseClass.copy method is essentially the builder pattern on crack. What you can do with it is you can say, hey, given this current state that I have, I want to take this little set of changes and apply it to that state and get a whole new state for me. So you'll notice that this pooler has a few data fields in it. And what I'm able to do is say, well, this pooler knows how to learn, and it will return a new pooler that's basically a copy of itself with just the connections modified. So all I had to do was take this .copy and then just give it the new connections map, and we're done. Right? So this pattern actually works beautifully for these nested data structures. That's one thing. Another one I should probably mention is, how many of you guys have used mapValues on a map? Okay, a few, not everybody. I learned something about mapValues. It was a valuable lesson, and so if I just save one person like a couple hours of frustration by sharing this, then great. Let me pull up an example. So I thought that mapValues was just a convenient version of map, but it actually does something else. What it does is it saves a copy of the original map plus an operation on that map. And so it's basically lazily computing these map values. So that's fine. But if you have this pattern where you're taking these case classes and you're repeatedly applying these updates, they stack up. And so I had something like this where I had a case class with a map in it, and I called .mapValues on it. And when you do this 1,000 times, your JVM is just going to go bonkers. So word of warning, read this article I have linked on the slides if you're curious about this. Okay, so let's go and talk about the flow of the data. Where do we start, right? So we start with this very simple trait called an encoder. So what the encoder does is it just takes whatever type of data from the outside world that you're trying to feed into this algorithm, and it turns it into an SDR, right? So that's pretty much all it does. I can show you guys an example of that in a little bit. So you start with your text or your image or whatever data set you're trying to learn, and you encode it into an SDR. Given that you've constructed a model, the next step is you feed it into this top level, hey, just process this input. And then what this does is it feeds it into the hierarchy. There's also a little bit of parallelism happening here that if there's time, I can explain what that is. But the gist of it is it's going to loop through all of these layers, and for each layer it's going to say, well, to what degree does the layer poolers overlap with the input? And all of those that have some overlap are now candidates for competing in this inhibition race. So they do this competition, and then they learn. And then you get back a new model. One thing I should also mention, just another brief digression about the encoder and streams. Let's see. Streams, yes. So in order to do like a training set where, let's say, you're learning some text, maybe you have a whole bunch of training examples, it seems convenient to stick it into a stream, right? How many of you guys use streams? Okay. So there's like a little dirty secret about streams. Yes, they're lazily evaluated data structures, but they're also memoized. So if you're holding on to a reference to the beginning of the stream, you're going to run into some trouble if the stream gets too long, because you'll have some GC issues, I'll tell you that. So in my slides, there's a link to a lovely 3-part article on the 5 things you must do to avoid this situation. But I thought I would, let you guys know about that. Okay, so that's the high level of the code. At this point, we can kind of do a choose your own adventure. So I want to get your thoughts on whether I should A, show you guys a demo, or B, talk about how we can parallelize the layers. So how many of you guys vote for the demo? Okay. How many of you guys vote for the parallelism? Okay. Okay, so I'll do that one if there's time. Okay. So let me just explain what this is first. This is a really simple, I was trying to make it like totally accessible. So this is, we'll play a word game. So we're going to take the top 1,000 most popular English words. And we're just going to feed these, we're going to encode these words as SDRs. And here's how we're going to encode them. Sparse distributed representation. That SDR is just the quick way of saying that. Okay. So we don't actually care what these words mean. This is the words, we could be any pattern. It just happens that words make sense to people. So don't think about the semantics or the meaning of the words at this point. So we take the individual letters in each word, and we're going to encode them into this SDR, which is the input. So the word free has unique letters FRE, and we're just going to say, well, F goes to, that's my mouse. F goes to this active bit, R goes to this one, and E goes here. And same thing for tree. Couple things to notice about this. One is it preserves the property that similar patterns have high degree of overlap. So the purple is really, hey, these two are shared. And then it's also distributed across this sparse vector. And it's stable. So every time we see an F, we're going to use this same slot. We're not just going to randomly pick the slots. We're using the same one every time. So this is the input to the algorithm, and it's just going to learn the coincidences. What are the letters that commonly happen together in these words? And so I kind of built this little example where you can take a partial word and a couple letters and just feed it to this thing and see what poolers match it, And then what you get back is what words have those letters in them. So let me show you that. So it's pretty simple. So we're going to create a model. I have this already set up. So we're just going to train it on 10,000 iterations. And it sits there. It takes a couple seconds. Okay. So we have our model now, and we want to kind of see what we want to query it and see what is it going to give us back. So we just give it a couple letters, let's say THE, since those are pretty common, and see what it gives us. So we get some output here. So what are we looking at here? What we're looking at is when we fed this demo, the THE letters, what poolers actually matched those letters. So it turns out that there was a pooler that decided that THE as letter combinations were common enough to stick together. And then what you see here is, what are the words that basically have all the letters of the pooler. So, you get a pretty decent match, and you can see the longer the word, the less similar it is. Because we're doing inhibition, there's actually two winners. So the level of sparsity kind of depends on the setting. So the sparsity level we have is there can actually be two. So the second best match had THE and A, right? So it was a slightly wider match. So you can kind of see how this is not limited to only exact matches. So it's finding some other letters there. We can try one more, just to get the idea. And then we've got, in this case, we have another pooler that matched CAN exactly, and there was one that was a little different. It had A and M. So it's basically trying to pick out, what are these best matches, and basically do some inference off of that. Let's see how we're doing on time. So I've got probably 10 minutes left. Okay. I can actually talk a little bit about parallelizing it. So, question? Yeah.
The problem you solved with it, is it something like if you looked at a word that wasn't in a dictionary, then it would find something that's kind of close to it, so it's like filling in the gaps in the background?
Yeah, it's trying to fill. It's basically. I chose the examples badly because those were actual words. So you could have given it a couple of consonants, right? And then it would have been able to fill those in, basically. That was the idea. Yeah, it's basically trying to it's finding what are the common letter combinations in these words, basically. That's a great question. The way that we're creating those SDRs are order invariant. We would have to construct the SDR so that you have some sense of order encoded in there if you wanted that ordering. Sorry, I didn't repeat that. The question was just a very astute observation that we're kind of order invariant, that can we make it so that order actually matters, right?
That's great for accurate, right?
What's that?
That's great for solving accurate, right? I was just
Yeah.
going to say, I think you just created some white people to cheat the crosswords.
Okay, so I can show you guys how to parallelize this. What's the basic idea? So I had to scrap the whole idea where each individual pooler was kind of this async thing, because really what's happening is you're doing stuff across this layer, right? You're inhibiting, and inhibition algorithm needs to look at several elements across the layer. So the unit of parallelism we're actually going to do is by the layer. So you don't really get an advantage unless you have multiple layers. So each layer can independently process its input. So let me go back to the model class and sort of explain what this is. This is the first time I've ever used RX Scala. So probably somebody else in the room will be like, no, you should do it that way, and that's fine. I would love to hear that. See me afterwards. So I'm just basically creating this observable factory thing. So what it is I only have one use case, which is do a bunch of stuff in parallel, right? Given an iterable of things that need to be transformed from one thing to another, apply this function, and each application is really a parallel execution. Hopefully that made sense. So I'm creating a observable. It basically creates an observable here. So it's using a thread pool executor under the hood, and basically creating a future on that. And then what you want is to return when all of these parallel tasks are complete. So that's basically what this does. So in the model, essentially, I am creating this process layer as my job, right? That's the function that's going to get executed on each layer. And then basically, it's creating one observable for the entire task, but each task is happening in parallel. And then basically, because this is all happening in this sort of command line way, I'm converting it to a blocking so that once everything is done, I can get it out. So hopefully that made a little bit of sense. Yeah. Okay, I should probably wrap up pretty soon. So let me go back to these slides. Okay. All right, so what? Okay, we built this thing and it does this cute little thing with letters, right? So what? There's a pretty awesome field of machine learning that solves some pretty hard problems and is making a big impact, looking at tagging images, looking at translation, NLP, all of these great things. So why do we need this other thing that does some kind of inference? So the goal is actually beyond that. Inference is really one step along the way. So the goal that we're actually striving for is intelligent behavior. And the idea is, I love the way this sums it up, right? Our brains are programmable and we are the programmers, right? Through our very actions, we are programming our brain. And so we want to build a machine that actually has behavior and has action. So as it turns out, these fundamental building blocks that we talked about today are a key piece of that. And creating a machine that can have action is kind of doing inference in reverse. You form predictions, you have a memory of time, and you act those out. So if you have questions and want to follow up on anything, here's my contact information. All of the code that I started stepping through today is available on GitHub, so you can, once you get the slides, just click the link and you can play with this little code example that I made. And I thank you for listening. So I think we have 5 minutes, so questions, Hugh. Yeah, it is. As a matter of fact, so the question was just the layering. Are you talking about on intelligence? Yeah, so is the layering the same type of layering in that book? Yes, absolutely. Question?
I'll speak loud enough so it doesn't need to be repeated, I hope. So I just wanted to point out that whether or not the brain actually works this way, whether there is a single rule for how the brain or a single algorithm, this may nonetheless, even if it's wrong, be very useful, or even if it's right, run into pitfalls because of the differences in architecture. The machine learning field, for example, deep learning comes from perceptrons, which were based on the idea of how neurons ought to work. And there are a lot of aspects of how they work, like backpropagation, which sort of don't really fit with a lot of neurophysiology. It doesn't matter because it's great for solving some problems.
Yep.
And inspiration is helpful.
I'm really glad you raised that point. You can get your bribe after the show. because I actually forgot to make that point, which is that we're not actually trying to literally build a brain, right? We're trying to build something that performs under these principles, and we're sort of borrowing from, we're not trying to get into the nitty-gritty of neuroscience, we're trying to glean out what are the organizing principles here and implement those and not worry too much about exactly matching biology. So, yeah, in the back.
I'm just curious if you mentioned in the one slide that you started out with an accurate implementation and that went horribly wrong. I'm just curious what went horribly wrong, because it seemed like, when you started talking about hierarchies and all of that kind of, and all these things working together in parallel, it seemed like a natural fit. So I'm just curious what fell apart when you tried to do that.
It was timing, given the asynchronicity of, it wasn't really possible to orchestrate inhibition across all these given the uncertainty of the timing of when would these inputs arrive. So it was unclear, where in the timeline are you? So that it was, and I don't think that ACA itself was a problem. I think it was just an ill-posed way of solving the problem by putting these poolers in such their own actors. So I would put an entire layer would be in its own actor. That might actually work. Anything else? No? Okay, well, thank you, everyone.